I have time and again said, sort of offhand in our course, that the choice of coordinate system is completely arbitrary, but can be to some advantage. So what I'm going to do today is show you how a choice of coordinate system can be of spectacular advantage in problem solving. It takes a little bit of cleverness to see how it applies, but once a good choice is made, the results can be very, very useful. And this particular technique that I'm going to show you today is going to be of value for you going forward. So here I have, what I'm going to do is show you a solution to an elastic collision problem. And I already know how to do that. So I'm going to go through it rather rapidly just to demonstrate the technique that you're already aware of and draw some conclusions from an elastic collision. And then after I've done it, I'm going to show you a different way to solve the problem that is just frankly stunning. Stunning in its simplicity. So let me begin. I have these two objects, A and B, we're familiar with, and they have velocities VA and VB accordingly here. Now I'm going to arrange it inside. We've seen this before, and I made the velocity of B 0. But now I'm going to give B a velocity, and so I'll select some values here. Let me let the mass of A be equal to 1 kilogram, and the velocity of A be equal to 2 meters per second. It's critical that I choose the velocity of B to be a lower velocity, otherwise A will never overcome B, and there won't be an collision at all. So I'm going to set the velocity of B to be 1 meter per second, and its mass to be 2 kilograms. Just chose those numbers. I kind of like the symmetry of it from an aesthetic point of view, but those are numbers I just chose. And what I endeavor to find out is, what are the velocities of A and B after the collision? Well, I understand now that I have the law of conservation of momentum, that when these two objects collide, that there's a quantity, the momentum, that I can calculate. There's a conserved quantity. So I'll begin by writing the law of conservation of momentum for this two-object collision. So I write that MAVA plus MBVB is equal to MAVA prime plus MBVB prime. And so immediately I'll fill in some answers here. Since MA is 1 and VA is 2, that's 2, plus MB is 2 times VB is 1, is 2 plus 2 is 4. So I have 4 Newton seconds of momentum on the left-hand side of my momentum equation. On the right-hand side, I know that the mass of A is 1, but VA prime is unknown, so I write VA prime, plus the mass of B is 2, so I write 2 VB prime. And that is my conservation of momentum equation with as much numbers plugged into it as I have available to me. VA prime is unknown and VB prime is unknown, and so I cannot solve this one equation because there are 2 unknowns. So I need something else in order to get my solution, and that something else, of course, is the law of conservation of energy, which I'm saying that I can apply because I've said that it's an elastic collision. And characteristic of elastic collision is that the energy is conserved. So what I'll write in addition to my conservation of momentum is a sort of conservation of kinetic energy. There are no potential energies involved in this situation. So however much kinetic energy I have in the beginning, that's how much kinetic energy I should have at the end. And so I write 1/2 MAVA squared plus 1/2 MBVB squared is equal to 1/2 MAVA prime squared plus 1/2 MBVB prime squared. I've simply added the initial and final kinetic energies. On the left-hand side of the equation, I have enough information to compute. But before I do that, let me cancel these 1/2s that I have in every term. No need to overcomplicate things. So I have MAVA. Well, VA is 2. 2 squared is 4 times 1 is 4. MB is 2 times VB squared. Well, VB is 1, so that's 2. Is 4 plus 2 is 6. So I have 3 joules of initial kinetic energy. Not 6 because I've canceled the 1/2 out, but I have 3 joules of kinetic energy, and I expect 3 joules after. So on the right-hand side, I have MA, which once again is 1, the VA prime squared, which is unknown, plus the MB is equal to 2, and the VB prime squared, which is unknown. So once again, I have an equation that has the 2 unknowns in it, the final velocity of A and B after the collision, which is what I endeavor to find, to understand. And so I'm going to solve these 2 equations simultaneously. A couple different ways to proceed, but for me, the most familiar way is to take my momentum equation and solve for the easiest thing to solve for, which obviously is VA prime. I'll solve for VA prime by subtracting 2 VB prime to the other side. So I have VA prime is equal to 4 minus 2 VB prime. I'm going to substitute that into my energy equation, but in the energy equation, it appears squared. So I'll square it first before I insert it. So VA prime squared is equal to the 4 minus 2 VB prime multiplied by 4 minus 2 VB prime. So I have to FOIL it. 4 and 4 is 16, and then I get 2 cross terms that are 8 VB prime, and that's negative 16 VB prime plus negative 2 VB prime times negative 2 VB prime, which is positive 4 VB prime squared. So I FOIL that out, it becomes something looking a little quadratic there. And now I'm going to take that, which I know is equal to VA prime squared, and I'm going to substitute it into my energy equation here. So here comes the energy equation. And what I'm going to do is take the energy equation with 6 is equal to VA prime squared. Well, now I'll plug in what I know VA prime squared is equal to, 16 minus 16 VB prime plus 4 VB prime squared. Not forgetting to add from the energy equation 2 VB prime squared. And so here I have this ultimate equation that has the virtue now of having only the unknown VB prime squared, well, VB prime, which appears both squared and unsquared in the equation. A little bit of simplification of this and rearrangement. I have 4 VB prime squareds plus 2 VB prime squareds, which ultimately is 6 VB prime squareds. I have a negative 16 VB prime term, and then I subtract this 6 over here. Subtracted from 16 is 10, is equal to 0. And so I see that I have an equation that is quadratic in VB prime squared. So I have to solve this quadratic equation. Then I know the solution to any quadratic, of course. Well, let me do a little simplification first because it's a little, I'm doing the head math here, so I have to be careful not to push my multiplication skills. I'm good at math and terrible at arithmetic. So I divide the whole thing through by 2. So 3 VB prime squared minus 8 VB prime squared plus 5 is equal to 0. Now apply the quadratic formula. To find the roots of this, I know it's negative b plus or minus the square root of b squared minus 4ac over 2a. And so plugging those numbers in, I'll have that VB prime is equal to negative b, which is 8 plus or minus the square root of 8 squared is 64, minus 4 times 3 times 5, divided by 6. Well, if I do all that a little arithmetic down, I get 8 plus or minus 2 divided by 6. Naturally, there are 2 roots to this quadratic. There are 2 possibilities and that's because of the square root that appears. So there are 2 roots to this. Those roots are, if I do 8 plus 2 divided by 6, that's 5/3 of a meter per second. That is one possibility for the final velocity, VB prime. Or, if I subtract 2, I get 1 meter per second as a possibility. So there are 2 roots, 2 possible values for VB prime. I have to choose which one is the appropriate one. You know, very often we do a projectile motion problem or whatever. We solve for time and it's quadratic and one of the answers comes out negative and you say, well, I can't have negative time, so I throw that one away and I use the positive result. I need some physical reason why it should be so that I choose one root over the other. Well, this one's fairly clear. Imagine that I make a guess and I say that VB prime is equal to 1 meter per second. That's a curious choice, because the initial velocity of VB was 1 meter per second. There's no way that VB is moving along at 1 meter per second, gets hit from behind, and continues to move at 1 meter per second. That's not possible. And so this root of 1 meter per second, of course, is unphysical, which means that I've found the value VB prime, which is 5/3 of a meter per second. Once I know VB prime, getting VA prime is easy to do because I already have an equation up here at the top that says that VA prime is equal to 4 minus 2 VB prime. And so I just have to use that equation. I'll write over here, VA prime is equal to 4 minus 2 VB prime. I'll plug in VB prime as 5/3. So I have 10/3 and 12/3 here. So 12/3 minus 10/3 is 2/3 of a meter per second. Notice that this makes physical sense too, because A is coming along with a velocity of 2 meters per second and runs into the back of B, therefore experiencing a force opposite its direction of motion. And so my expectation is that A should, at a minimum, slow. A should slow down. Now, it's possible that I choose the masses and velocities such that not only does A slow down, but it turns around completely and goes in the opposite direction. I could get a negative answer for VA prime. I could get a negative answer, but in this case, VA slows from 2 meters per second down to 2/3, and I like these answers. VA prime is 2/3 of a meter per second. VB prime is 5/3 of a meter per second. And so I found the velocities after collision, this elastic collision, by appreciating the fact that I can write the law of conservation of momentum, conservation of energy, and then a little bit of algebra and arithmetic, and out come the answer. That was laborious. If I had my druthers, I'd really rather not do that on a test. It's lots and lots of arithmetic. Perhaps there is a better approach. We say, yes, Shidley, you already told us what the better approach is. A way that I could go about this is I could say, well, look, the velocity of B is 1, but let me transform into a coordinate system where B is at rest. I would do that by subtracting 1 from every velocity in the problem. So VB would become 0 and VA would become 1 meter per second. We say, well, their masses aren't equal to each other, but I can fix that by saying ma has half the mass. Let me say that ma has half the velocity. So if I make this a velocity of 0.5 and I make this a velocity of 0, then I know what happens in the collision. They exchange. And then I'll do the collision that way, and then I'll add 1 to them all, and then I get the answers out. That's a clever way of doing it, by transforming into a coordinate system where I already know the answer. That's a better way of solving the problem, a smart way of solving the problem, by choosing a coordinate system that moves along with the object B, which transforms it into a problem that I already know how to solve. Boy, isn't that clever. Believe it or not, quite surprisingly, there's even a better way to solve the problem. It's quite remarkable, and I'd like to show you. So what I'm going to do here, if I can find, is I'm going to erase all of this solution and just ask you to appreciate. I'm going to erase all the solution. I'll leave the setup here. I'm going to do the exact same problem again, but I'm going to try a different approach, and the approach is going to have remarkable simplicity. So I'm going to erase here all of this algebra that I did, all this terrible, terrible, terrible algebra, including quadratic formula, which for some reason young people really, really, really don't want to do. And I'll erase this bit here, but I'll leave the answers, because it's really important that if I show you a different technique, that I get the same result, right? Because the right answer is the right answer is the right answer. So I'll leave that there. So the pressure's on me to get the same answer. I'm going to solve this problem in a different coordinate system. Right now, I propose the problem as A is moving with a velocity of 2 meters per second and B is moving with a velocity of 1 meter per second, and we're making an assumption. The assumption is that I'm standing here and you're all sitting there, and we're watching them go by. In fact, if I could animate the board, which of course I can't, sometime for the future, I guess, I would see them going along like this, and the collision would take place and the whole thing would move. The whole thing would move from the left to the right, and it would travel across the board, and I'd see the collision take place and go like that. Our frame of reference in physics is sometimes referred to as the lab frame. We imagine ourselves to be at rest, and the apparatus, in this case the two colliding objects, moves by us with the velocities that we measure in this frame of reference, at rest relative to what's going on. Now, of course, special relativity in the future will talk about there being no preferred reference frame. There really is no rest frame. But the frame of reference in which we typically solve this problem, which this problem is taught in lower level physics classes, is called the lab frame. So here I am in the lab frame of reference, and I've solved the problem. I can use any frame of reference that I choose. It's completely arbitrary. So I'm going to choose to do something quite remarkable. I'm going to transform into a coordinate system that moves along with the center of mass location of these two objects. That's a pretty trippy statement. I think you're on board with the idea of me transforming to B. It's like you're riding on B. When you transform to B, now B's at rest because you're standing on it, right? And A approaches and they collide that way. Right? You transform to a coordinate system that's at rest on B, that forces B to be at rest, at least until after the collision. Now, imagine as A and B move along and they approach each other and they collide, as you're watching it go by, imagine the center of mass location. It's somewhere here between A and B. It's somewhere between A and B. And because B is more massive than A, I know it's somewhere closer to B. So as it goes along, see if you can animate it in your mind. As it goes along, two things will happen. The center of mass position will always remain between A and B. It's got to be in there somewhere. And it will grow ever closer to B, and will always be closer to B because of the way the center of mass is defined as the weighted average of position. So now, let's take our coordinate system and transform to a coordinate system that rides along with the center of mass. Now you're standing at the center of mass position. Use your mental horsepower to imagine what this is like. You're standing at the center of mass position. Now you will always be between A and B. Where does the collision of A and B take place in your coordinate system? It takes place at the center of mass, because the center of mass is always in between. And so as A and B come at each other, and realize the implication of that is that A is coming at you from the left, but now B is coming at you from the right. From the center of mass point of view, you're standing at the location where the collision is going to happen. It's a little prescient knowledge of what's happening in the collision. You're standing where the collision will happen. They will come at you and collide. Bang! Right where you are. And then what must happen after collision? They must turn around and go away from you. Because after the collision takes place, you're still standing at the center of mass location, and they are going away from you. But you have to remain in the middle. And so they both go off away from you in opposite directions. The law of conservation of momentum for a system tells me that the sum, or the net external force, is equal to the mass times the mass times the center of mass acceleration. This is what I established yesterday. The mass times the center of mass acceleration. And also I established yesterday that the total momentum of the system is equal to the mass times the center of mass velocity. There are no external forces acting here, which means the change in momentum of the system is equal to 0, which means the momentum of the center of mass is a conserved quantity. As these things collide, the center of mass position will move along before, during, and after the collision with exactly the same velocity. The center of mass position cruises along with constant momentum the whole time. Constant momentum the whole time. The momentum of A changes during the collision. The momentum of B changes during the collision, but the momentum of the center of mass is constant the entire time. And so the velocity of the center of mass is constant the entire time. So standing on the center of mass, watching the collision happen, you cruise to the right constantly the entire time. There's another beautiful consequence of this. When I stand at the center of mass, because the masses of A and B are fixed, the distance from me to A, which is over there, and the distance from me to B, which is closer because more massive, those distances are determined by the weighted average of position. Their ratios have to remain fixed, which means if they're going to arrive at my location at the same time, in my frame of reference, B has to be moving slower because it has less distance to go. It has to be moving slower because it has less distance to go. A has to move faster. You got to get over here. We're having a collision here at the center of mass. You better get here. It's got to go faster. And then after they collide and they travel away again, A has to be further away than B in the same amount of time because B has to be closer because of the center of mass condition, which means that A has to travel away more rapidly in order to be further away in the same amount of time, which means in the center of mass frame, and this is the key to the whole thing, this is the wonderful, splendid thing about it. In the center of mass frame, when the collision takes place, the only thing that happens in the center of mass collision is the objects reverse their velocity and take off in the opposite direction after collision. It does not matter what their initial masses and initial velocities are. You're standing at the center of mass frame, so they come at you with velocities, they collide, and they travel away from you with the same speeds, not velocities, because the signs have reversed. So when I do a collision in the center of mass frame, an elastic collision, by the way, when I do an elastic collision in the center of mass frame, all I have to do is change the sign of the velocities. That's the only calculation I have to do. Let me go ahead and do that calculation and demonstrate to you what happens. So the first step is going to be, to solve this problem in the center of mass frame, is to transform myself to a coordinate system in the center of mass frame. That involves subtracting away the velocity of the thing that I want to transform to. So I have to subtract away the center of mass velocity, which means I have to calculate it. I have to calculate the center of mass velocity. Well, I know how to do that. The velocity of the center of mass is the derivative of the center of mass position. So I can calculate the center of mass velocity quite easily. It's going to be MAVA plus MBVB divided by the total mass, MA plus MB. Calculating the center of mass velocity is quite a simple task to do. And in particular, in this case, the numbers are quite simple, so I'm even luckier in that regard. So I have MA times VA, so it's 1 times 2 is 2, plus MB times VB is 2 times 1 is 2, so it's 4. You say, Sally, you already calculated that because you did conservation of momentum already, and that's the same thing that happened. No, that's true. The masses are 1 kilogram and 2 kilograms. That's 3 kilograms. So I find that the center of mass velocity for this system is 4/3 of a meter per second. That's step the first. Now I'm going to transform into that coordinate system that rides along with the center of mass velocity. In order to do that, I have to subtract the center of mass velocity from the initial velocities. So I'm going to take the velocity of A, and I'm going to transform the velocity of A into the velocity of A in the center of mass frame. I'm going to add some notation to keep that clear, okay? I'm going to star quantities that are in the center of mass frame. So VA star means the velocity of A in the center of mass frame. Well, VA star, the velocity of A in the center of mass frame, is equal to VA minus the velocity of center of mass. And you know this because we've already realized and understood that to transform into a moving coordinate system, I subtract the coordinate system velocity away. And so I'm subtracting away. Now, VA originally was 2, so it's going to be equal to 2 minus 4/3. Well, that's 6/3 minus 4/3 is equal to 2/3 of a meter per second. So the velocity of A in the center of mass frame is 2/3, and that makes sense. That makes sense because A is coming at me, so I'm going to observe that in the center of mass frame as a positive velocity. So I like that it's a positive velocity. And also, I'm riding with the center of mass, which means I'm scooting to the right, which means A coming at me is going to appear slower than it does in the rest frame. So everything's physically appropriate so far. But I also need to calculate the velocity of B in the center of mass frame. And so I'll take VB, and from VB, I'll subtract away the center of mass velocity. From VB, I'll subtract away the center of mass velocity. So when I do that, I have, what was VB? It was 1. So I'm going to have 3/3 minus 1/3 is equal to, 4/3, pardon me. Thank you. I realized something was going terribly wrong there. Oh, and now oh boy. 4/3. So 3/3 minus 4/3 is negative 1/3. I get alarmed for half a second. I'm like, whoa, it turned negative. But no, that makes sense. I'm standing at the center of mass location, and so in order for the collision to happen at my location, B must be approaching me, and therefore traveling in the negative direction. So that I get a negative velocity for B here makes an awful lot of sense. Now, conservation of momentum? Who needs it? Well, actually, we need it, but it's hiding underneath because I've realized that in the center of mass frame, when objects collide, the final velocities after collision, they've just reversed direction. They've just reversed direction. Which means that, I think I'll go to the middle of the board here, that the velocity of A in the center of mass frame after collision, how do you like that, VA star prime? The velocity of A in the center of mass frame after the collision is going to be equal to the negative of the velocity of A in the center of mass frame. It just reverses direction, which means the velocity of A in the center of mass frame after the collision is just negative 2/3 of a meter per second. And that makes sense, because here I stand at the center of mass frame, the collision has happened, now A needs to be going that way, in the negative direction, away from me, to the left. So negative 2/3 of a meter per second. Now the velocity of B in the center of mass frame prime is equal to the negative of the velocity of B in the center of mass frame initially. Now in the center of mass frame it was negative 1/3 of a meter per second. Now it's going to be positive a 1/3 meter per second. And that makes sense, because after the collision happens and I'm standing at the center of mass frame position, it must go off in the positive direction to preserve that whole center of mass algebra. But there you go. So I found the velocities after collision, but I didn't find the velocities that we wanted after collision. I found the velocities in the center of mass frame after collision. I want them in the rest frame. I want them in the lab frame. I want the answers to my question. So what I have to do, I subtracted the center of mass velocity to transform into this coordinate system. I'll simply add the center of mass velocity to transform out of this coordinate system. And so the velocity of A after the collision is going to be equal to the velocity of A after the collision in the center of mass frame, VA star prime, plus the center of mass velocity, which is going to be equal to negative 2/3 plus 4/3, because recall the center of mass velocity I calculated at the beginning is 4/3 of a meter per second, is equal to 2/3 of a meter per second. And it's okay to get excited at this point because that's exactly the result that I got doing it the other way around. Now the velocity of B after collision is going to be the velocity of B in the center of mass frame plus the velocity of the center of mass, doing the same thing, transforming that velocity out of the frame. So I have 1/3 of a meter per second, which is the velocity in the center, final velocity in the center of mass frame, plus the center of mass velocity, which is 4/3, is equal to 5/3 of a meter per second. And once again, I've found the velocity that is the result by transforming the center of mass frame. And you say to yourself, maybe, you say to yourself, well, Shadi, that was kind of a lot of work too. Well, it was only a lot of work because I was teaching it to you. Now let's go through it and put the steps together. What did I have to do to make this happen? What did I have to do to get V prime? Notice I didn't say A or B because it's the same process for A and B. So what did I do to get a velocity after collision? Well, the first thing that I had to do to get a velocity after collision is I had to take the velocity before the collision and subtract the center of mass velocity from it. That's the first step that I had to do. I had to take the velocity before the collision and subtract the center of mass velocity. And then I had to reverse its sign, right? And then I had to reverse its sign, so I slap a negative sign on there. And then I had to add the center of mass velocity to it. And then I had to add the center of mass velocity to it. Well, the negative sign outside this quantity here is simply going to reverse the order of the quantity. So it becomes VCM plus VCM minus V, which means the velocity after collision is equal to twice the center of mass velocity minus the initial velocity, and I can calculate velocities after an elastic collision in one go. And if I can calculate the center mass velocity in my head, I can do this in my head. I can simply look at the problem, read the initial velocities and the masses of the particles, calculate the center mass velocity, twice the center mass velocity minus the initial velocity, answer. That is an extraordinarily powerful use of coordinate system choice to dramatically simplify the solution to an otherwise algebraically knotty and somewhat inconvenient problem.